Um, okay, glad you didn't record what I said just before.
I started at the right time.
Good, good. So we talked about the combination of three factors that powered the new rise of AI, namely the abundance of data, the high performance computing, and the new algorithms. Oops. Also, as I said, I talked about the precision medicine and how machine learning is capital to do such a thing like precision medicine. Talked about what is precision medicine. Anyways, I also said that there were many achievements, notable achievements with AI, and we have a list here. We went through the list. I'm trying to go fast. Then we talked about the singularity, the technological singularity, and my view is that there are different ways of getting there. What is there? There is when we have basically an entity, a machine that is more intelligent than humans and will actually be driving the innovation in our society. And we can't predict actually how that will go. And there are four ways. One is to help biology, help nature to basically evolve faster towards something that is more intelligent, but that will take a very long time. It's completely unethical. There's the number two is the creation of a machine, an AI that is better than us. Third one is to merge with this machine. This is the cybernetic singularity. And the fourth one is some kind of intelligence that could rise from the collective of interconnected smart objects, what we call the Internet of Things. And what control would we have? Well, we don't know. I'm betting more on number three, and I gave you some arguments. Then I don't know if we mentioned, I mentioned this, the importance of computational intelligence is not just building this machine that can do amazing things, a tool for us, but also understanding our own intelligence. What is intelligence? Still a debate. And it's not a new debate. I mean, people were debating about intelligence from the Greek philosophers. Since we recorded anything, we were debating that already. So one interesting piece of work is by Alan Turing in 1950, who wrote an essay about intelligent machines. And this was 60 years ago, 70 years ago. And he was imagining a way to decide whether a machine is actually intelligent or not, intelligent like humans. And he devised this game that he called the imitation game, and predicted that by year 2000, so 50 years after he wrote this, he actually died, I think in 1954, so 4 years after he wrote this. But he predicted that by year 2000, a machine might have a 30% chance of fooling a common person for at least 5 minutes. What does it mean, fool a common person? It means a person would not know if it's a machine or a human that is communicating with it. And the game is as follows. You have a machine or a human on one side of a wall or curtain that is communicating. So one of these two is communicating with another human, a judge. And if this judge doesn't know whether he or she is communicating with a human or a machine, and if it is a machine, then the machine is smart enough, intelligent enough to fool this human. And that was very interesting. And many pioneers in AI were interested in building such a machine to try to fool a human. And one of the first chatbots, very famous chatbot, is Eliza, done at MIT in 1966. So a long time ago. Relatively simple chatbot because it's based on rules. a person says an utterance, a sentence, and some keywords may be recognized. And if a keyword is recognized, found in that input, we can match it to a rule, and that rule will generate a sentence as a response. If no keyword is found, then there is a generic kind of response that is returned by Eliza. And Eliza had hundreds of these built-in rules to be able to have this dialogue. I'll show you an example of a dialogue. Eliza simulators still exist online. You can find them. This is a simulator built in 2005 using the rules that were defined by Weizenbaum in 1966 at MIT. You can see the kind of, the style of responses. So one version of Eliza was doctor, and doctor was like a psychologist talking to a patient. And this is exactly what you will see here. Eliza is saying, is something troubling you? And the person is saying, men, are you alike? What is the connection, do you suppose? They're always bugging us about something or other. Can you think of a specific example? Well, my boyfriend made me come here. So there's a word boyfriend. That boyfriend will trigger a rule. Is it important that that your boyfriend made you come here? So taking the same verb and same place from the sentence, and it generates this. And you can see that these sentences are typically questions like a psychologist would do, and they're open kind of questions to invite you to say more. He says, I'm depressed much of the time. So I'm grabbing the verb, the word depressed, and I am sorry to hear that you are depressed. It's true, I'm unhappy. Again, unhappy is a word that will trigger a response. Can you explain what made you unhappy? And the conversation can go on and on and on for actually hours. And the interesting thing, many people love this and connected to the system to talk to Eliza, and people claim that they felt way better going to talk to Eliza than even a human being. But we can identify that this is a machine, not a human. But it was fun. But this led to a famous competition, the Loebner Prize. This is a rich guy who said, okay, if somebody can fool a machine, if a machine can fool a human out of 3, so that because Turing was saying 30% of chance. So if I have 3 judges and one of the judges cannot distinguish whether it's a machine or a human, then the one who built that machine will get $100,000. And of course, that attracted the attention to many people who wanted to build these chatbots. And every year there was this competition. I'll show you some examples of output. And you'll see it's not easy at all. This is Jabberwocky, was third place in the Loebner Prize in 2003, was 4th in 2008. The competition stopped, actually. It took a different focus because there was somebody who won the $100,000 at one point. Now I'll get to it. But you can go and try Jabberwocky at this address. Here's an example. What's your name? And I say, Fred. No, it isn't. And I've been trying. So I say, oh, how does it know? What do you mean? I'm lying? Yes, I'm a very good liar. One of the best. But I said, I am lying. And it says, I am very good liar. So it doesn't understand what it's saying and what I said. And that doesn't mean I'm a liar if you are a good one. Yes, it does. Why is that? I'm God. Oh my gosh, it's completely hallucinating now. Do you have a temple for you? No, that's all right. So you're God with a small g, because it says I'm God with a small g. I am small g. So you see that basically these responses are generated based on the previous message. And it doesn't understand the whole context of the conversation anymore. Its context is only the previous utterance. And the answers don't make any sense. And very easily you can see that it's not a human, it's a machine, or somebody who's completely under influence. Here's another example. This is Alice. Alice won the prize many times, many years. You can also go and try it. I don't know if these URLs still exist. Now, Alice starts, I'm Alice. Where are you? I'm asking. I'm in Auckland, California. Where are you? And I say, I'm in Canada. Tell me a little about your life in Canada. This looks good so far. It is cold, I said. I am warm here, because it's California. Where's the best Chinese restaurant? So I'm changing the conversation. And it says, I think it's a tie. Why is it a tie? Why do I exist? And there you go. It starts hallucinating, and it's completely out of scope, completely talking about something else. And then very easily you can see it's not a human, it's a machine. Okay. Because it generates things that are not related to what came before. Even though in the beginning, if you stop early, you say, oh my gosh, this is actually quite good. Remember, the challenge was to be able to fool 30% of the people, 30% of chance for 5 minutes. We have to continue having a conversation for 5 minutes and not knowing whether it's a human or a machine. This is another example with Cleverbot. Cleverbot also was the winner in 2008, but also won other prizes. You can try it here. Anyways, you can see it hallucinates at one point, even though it starts very well. I'm trying to go a little bit faster. This is the guy who won the prize finally, and you can go and try it here. This is a team that created this chatbot, but they added some caveat to it. They pretended that it's a young boy, 13-year-old boy from Ukraine. So when the judges know, hey, you're talking to a 13-year-old boy behind the curtain, you're a little bit more indulgent, especially coming from Ukraine. So if it makes mistakes in English, it's okay, and things like that. Well, you can go and try it out, and you can see that actually it will do mistakes as well, trying to go a little bit faster. So that was in 2014. They managed to fool at least one judge out of 3. And for 5 minutes, the judge didn't know that this machine was actually a machine and not a human. Today, we're very used to these chatbots. You have a chatbot on your phone. You can buy these smart speakers like Siri, Cortana, Alexa, Google Now, Google Home now it's called. There are many of them. Unfortunately, you can't have a fluent kind of conversation with these. They are mainly what we call task-oriented chatbots. They have a purpose, and the purpose is to help you with a particular task, typically to purchase some goods or services. So if you say, I want to reserve a table at a restaurant, then it identifies the intent. It's about restaurant, it has nothing to do with an air ticket or buying a book or something. So it has a template for restaurants, and to be able to answer you for that need, it needs to ask you other questions like how many people, what kind of food it is, when do you want to go, and is it close? Do you want to go far away or close by or something like that? Once it collects enough variables, then it can generate a query to a database and come back with an answer. If it detects a different intent that, well, you want to know the temperature of whatever city, then it'll do that particular task. They're task-oriented chatbots. It's not able to do a conversation like the other chatbots that I was showing you, except very, very limited canned, hard-coded conversations that are in the code. But beyond that, it's limited. So I am part of a team. I'm leading actually a team working on a chatbot for conversation, and this is targeting the elderly. This is before COVID and the confinement and people staying at home and being bored. But it seems that these people are also interested in having an agent like that. So this is an agent for companionship, but for the elderly. And we are trying to generate responses automatically. It's never the same. And the responses are based on previous context, the text that we have before. It's not perfect. There's many things that are missing. Like, for example, we are adding now the detection of emotions and the response based on that emotion expressed by the person. If I say my neighbor fell and broke his hip, well, first I have to express surprise and empathy and things like that. So how do you do that with automatically in the response? Detecting all the things as well. I'm not going to go into the details, but there are other issues. Like, for example, here, these are snippets from conversations. I'm showing you an example here where the user is asking, suggesting, should we go out? And the chatbot says, why not? Where do you want to go? Let's go to the park. What will we do there? What we will do there? It doesn't matter here, there are mistakes, but the chatbot can understand, we will play football and have a good time. But you can immediately realize that this is fantasy, because the chatbot, that small machine, will not be able to go out because it's not connected anymore. And certainly that machine will not be able to play football. And so we are able to generate responses that are syntactically correct and sound English and all that stuff, but they're not necessarily realistic. So how do you make them realistic? How do you ground them on some knowledge so they don't hallucinate and they stay on topic? And even if you change topic, you drift, like in our typical conversations, we drift from one topic to the other, and we can come back to the original topic. How to control all that is not trivial. There are other things that are not trivial, is how to make jokes. Here, this is the chatbot on the right-hand side. The left-hand side is the user. Two silkworms had a race. They ended up in a tie. Worms don't race. So this is actually a chatbot that is trying to identify things that don't make sense. So we taught it to recognize common sense and nonsensical things and respond to nonsensical things. But it realized that actually worms don't race. And that's a very good response. However, it missed the point of the joke here, because they're silkworms in a tie made with silk. And I say, it's a joke. I know. But of course, the chatbot didn't understand. Did you get it? Silk tie. It didn't. Here's another example. And humor is extremely complex. And as I'm saying here, it's a manifestation of intelligence for humans. It's very, very interesting. I will give you another one here. And then the chatbot answers, people don't get sick if they give someone a second chance. So, wow, this is interesting. It seems very appropriate answer for this circumstance. And then I give the joke, a dog gave birth to puppies near the road and was cited for littering. And the chatbot says, it's so disgusting. It missed the point that, again, is a joke. Even though I gave him a warning, I'll give you another joke. And littering and the litter of puppies, it didn't make the connection. And it's not easy to do. It's very, very complex. Anyways, that's about the Turing test. We're still far away from the Turing test. And many people are arguing that actually Turing test is not a good test for really assessing the intelligence of a machine. There are many there are flaws in the Turing test itself, but it's an interesting indicator, at least for chatbots. So now I want to go back to the AI, which has many subfields. One of them is machine learning. And we said in machine learning, we have supervised learning and other types of learnings like reinforcement learning and unsupervised learning and so forth. But I want to focus on, I'll zoom in now, supervised learning. One of them is deep learning, and I may mention that soon. Are there any questions before I dive into supervised learning? No questions. I'm just opening here the cameras of the others to see you. No questions, so I'll move on. Are there questions in the chat? Oh, so there's a hand.
Yeah, I just had a quick question about the chatbots. So, like, I was wondering because the way it works, it's like I guess the judge talks, and then the chatbot talks. So, is it like almost limited by I'm trying to think of how I'm trying to say this.
No,
Like, I feel like it's
no, it's not one utterance, one utterance. Sometimes it can be two sentences, and then the chatbot says something, and then the chatbot may not wait for the other to say an utterance, can give a second utterance. It's not always question answering. It can be statements. So, and that's another problem that the chatbot has to realize. Is it a statement? Like you say, the weather is beautiful outside, that's a statement, or it can be a question, what's the time, what's the weather outside? So that's what we call interrogative, or it can be imperative. Imperative is when I give it an order, turn on the light, call my mother, something like that. So these distinguishing between these is not trivial because we don't get punctuations. You don't necessarily get the question mark. You have speech that is translated into text. The chatbot receives text as input, and there's no punctuation. So yeah, when there is a question, you stop and you wait for the other one to respond. But when it's a statement, you can give a statement and then another statement and another statement, then you wait. So it's not necessarily one-to-one. It's a mixture.
okay. Yeah, because I was thinking if it was just one-to-one, then I feel like that's kind of hard to fool someone because it's not really conversational then. It's
Yeah, I don't know.
just-
I agree with you, but it is the case that it's not always one-to-one. But in these competitions, the person behind the curtain, if it is a person and not a machine, will respond the same way. If you ask a question, will respond. If you make a statement, it may wait a few seconds and give you one statement or two statements. So they behave the same way.
Okay.
Yeah.
Thanks.
But in the case of chatbots that we know, like these smart, what we call smart speakers that you have at home, it's typically one statement and then another. I ask it the question, I don't know, who's the president of the United States? It's a question, and then I wait until it gives me the answer. The answer can be elaborate. Often these chatbots, if they are on a tablet or whatever, it may even tell me, oh, here, I found you this answer from the internet, and it starts reading the snippet from a web page or something like that. Or if I ask it, give me the definition of whatever, it may find two definitions and it may tell me I have these two definitions. So it's not really one-to-one, but almost.
Yeah.
Any other question?
I just have a follow-up question kind of relating to that. So then how, like, was that kind of like a problem where like the punctuation and stuff like that? Because it's kind of hard to like tell like the nuances of like, am I saying this as a statement or a question? Like if say if the investigator or whatever, if they don't put the question mark at the end of the sentence. So like, is that something that was confusing?
No, it creates problems. So we have a classifier using supervised learning. So we give it many questions, many statements, and many orders, so imperative, and we label them. We say these are questions, these are, and it learns to recognize based on how the words are used in the sentence. It learns to recognize a question and distinguish a question from a statement. But it makes mistakes. Sometimes I ask a question as a statement. I make a statement, but actually it is a question. Like you're crazy. I'm expecting, well, that's not a good example, but anyways, you can imagine there are some questions. I'm asking the question by giving you a statement. And Chatbot, based on the technique that we provide to recognize these, since we don't have punctuation, may sometimes make mistakes.
Yeah, that makes sense. Thank you.
Yeah, mind you, humans do mistakes too, because I didn't hear it properly, or because I don't know the style of the other person, or because I don't understand the sarcasm sometimes. I mean, humans make mistakes too, and we repeat. So no, you didn't understand me. I meant this. So we want the same thing with the chatbot too. The chatbot that we are designing is not to fool the purpose is not to fool the user. The purpose is to be a companion. So the user will always know that it's a machine anyways. Okay. So going back to, and let me close this so I can see my slide. Okay. So I'm going back to this Zoom. I'm zooming in supervised learning to better understand, because supervised learning is the technology, the most used technology in these applications that I showed you before. Okay, those related to precision health, for example. So the idea of machine learning is to teach a machine to actually classify or predict how to label something. The analogy that I typically give is the following. Imagine you have a pile of balls with different colors, different sizes here. Unfortunately, they're not different sizes, but imagine they have different sizes, different colors, different structures, different weights. They have different characteristics, okay? And then I have, on the other side, I have buckets with different colors. And I have a child next to me. And the child is actually representing the machine. And I'll tell the child, watch me, what I do, and learn. And I grab a ball, I look at it, touch it, whatever, and then I decide to put it in a bucket. I do that with few balls. I don't know, 10, 20. And then I ask the child, okay, now you do it. It's your turn. Did you understand what I'm doing? Here's a ball, it's your turn. Where will you put it? Okay. So what feature was I using to decide where to put the ball? Was it the weight? Was it the size? Was it the color? Was it a combination color and structure? What was it? If the child was paying attention, the child will see that I took the red ball and I put it in the red bucket, the blue ball, blue bucket, the green ball in the green bucket, the black ball in the black bucket. So when I give it a ball, it'll just the child will have to look at the color and decide, okay, if it learned properly, it'll put it in the green bucket. So what did the child do here? The child learned to predict in which bucket I would put a particular ball given its characteristics. And it happens here that all the characteristics didn't matter except the color in this particular example, but it could have been something else. So learning means to learn the characteristics of some object that will discriminate it from the others. Here, the colors are discriminating these, and I will put them in these buckets. So putting them in these buckets is like labeling them. And what I was showing to the child is what we call the training set. I gave it some training because I gave it the ball associated with the bucket that I put it in. So what happens now is that machine learning, supervised learning, I'm given here a training set that is already labeled. The algorithm will go over it and find what distinguishes each class from the other class. The class here are labels, and will build a predictive model, a model that can classify these objects. Then I have new objects that haven't been classified. These are like the balls from the pile that I didn't put in buckets yet. These are all put in buckets. And I'll say to the child, okay, now this is what you learned. Use it to predict in which bucket I should put these balls. So which label should they be? See, here I have labels. This can be this type of cancer, this other type of cancer. So it can be different things. Here I have many labels. I could have only two classes, normal and cancerous and stuff like that. So an example here, I'm reducing this example into this one, my training data is a set of emails. Some of them are important, they're green, and some of them are spam, they're red. And then the algorithm will learn a predictive model. And then when I have new email, that predictive model will now label them for me automatically. These are important, these I'll dump directly in the spam folder. How did I give this? Well, it's my behavior. While I was reading and answering emails and saving emails and deleting other emails, I'm already labeling them for my classifier. So that's what happens. Here's another example now. I don't have emails, I don't have balls, I have actually mammograms. And the doctor will say, this mammogram is okay, this one has this microcalcification here in this region and so forth. So these are labeled, and then the program will go over that and will learn a predictive model to use when I have new images that haven't been labeled before, and will predict for me which one is normal and which one has these regions of interest. Okay. Of course, it's not as easy as that. There are many, many challenges. One of them is, what are the relevant features to consider when I'm learning, so that will distinguish between the different classes? What is the algorithm that will efficiently go through this and identify automatically these features that are relevant? How do you build this predictive model? I'm representing here by cloud, so that I can use it effectively later. So how do I effectively use that model now? Anyways, there are many open problems, and it differs from one application to the other. Now I'll show you some other applications, not just medical, where exactly the same technique is taking place, like in autonomous vehicles. Autonomous vehicles need to recognize, for example, there are many things that have to recognize. Is it a pedestrian crossing the street, or is it a plastic bag taken by the wind? I have different road signs. Is it a stop sign, or is it no left turn, or is it a speed limit sign, or how do I recognize the different signs? All that is done with machine learning. Another example, and this is actually quite old, it dates from the time when we started trying to read the postal codes on envelopes, or reading the amounts on checks that are handwritten. How do you recognize this 2 from that 2 from that 3? Is it a 6, or is it a B, or is it an 8 or a 9? Or how you do that automatically? That was done with machine learning, providing different handwritings and learning automatically to distinguish them. Now we can do even better, because we can handwrite mathematical formulae or handwrite in English, and we can automatically recognize the different letters or different pieces of this formula to rewrite it correctly. So all that is using machine learning. Machine learning is used for detecting spam. I mentioned that. Also for credit card fraud detection. When you swipe your card to get the authorization for a particular transaction, there is not on the machine here, but in the server of the bank or the credit card company, you have a machine learning algorithm that learned about your past transactions and sees if this is a kind of transaction that needs to be flagged for fraud. Financial applications, especially now the high frequency trading, humans cannot regulate this. You have machine learning algorithms that look at these transactions and flag those that need to be investigated by regulators. Well, I think I mentioned also this example in the past. When you go and ask for a loan at the bank, they have a machine learning algorithm that will predict whether you will actually pay back the loan or default on the loan, and based on that score, they will give you the approval or not. And how do they do that? Well, they learn on past customers and they compare you and your characteristics and the characteristics of the other customers that defaulted or not on their loans. Recommender systems use also machine learning to learn what you like and what you dislike compared to other people, what they liked and what they disliked. There are many kind of recommender systems, adaptive interfaces. Many of you are on social media. Some of you have hundreds, some actually thousands of friends or pseudo friends, and they all are active. And if you connect to Facebook, and if you on the wall, you'll see every single activity of everybody. It's impossible. So Facebook or the like, they will select activities of your friends based on what they predict that you will actually react to. So based on what you liked in the past, what you shared, what you responded to, and things like that, they will show you only those that have a higher probability that you will interact with. So this is also machine learning. Don't have the time to go through all of them, but well, I'll give you an example of the remote control. This was a few years ago. A company called Philips designed this remote control for the TV. When you skip channels, skip. If you have 500 channels, that'll take you forever, and you can't remember the numbers of all of them. So it observes how you skip channels and how you stop in channels. And then it may realize, oh, you like more the sports channels, for example, and then it'll skip automatically for you instead of going one by one. And then if there's another member of the family that has a different preference, they want to look at soap operas or whatever, then it'll skip differently for them. And they identify one user from the other with 4 different buttons, A, B, C, D. So you grab the remote control and you say, I am B, and then it learns when you're trying to skip channels, it'll jump to those that you really like and save you time. So there are many applications like that that learn from your behavior and do predictions with supervised learning. So in medical applications, we have many examples last time. I'll go over this again very briefly. So you have a novel patient, you want to predict, for example, if a particular, in this case, cancer, if cancer will reoccur or not. Well, you look at historical data from other patients for which you know the label. So these are the balls, and these are the colors of the, oh, no, I'm sorry, these are the buckets where we will put the balls. One of these here is the color, some others are the weights and the friction and whatever, all sorts of characteristics of the balls, but we don't have balls here, we have patients. But basically we learn based on this data to build a predictive model, and this predictive model is the child. I give it a new ball and it'll tell me, oops, it'll go in this particular bucket. Here I have only 2 buckets, the yes and the no. Okay, it will say, no, it will not recur based on these characteristics and what I learned from past patients. Now, there are distinctions. When I gave you this example here, I said there are many, it could be many classes. This is what we call a multi-class classification problem. I learn a model to discriminate between many classes, but many problems are what we call binary class or binary classification. So on the training data, I have only 2 labels. Okay, so my classification is learning a model to distinguish between 2 classes, binary classification. Is it normal or sick? Or is it spam, non-spam? So typically you have 2, but there are many other applications where you have many classes. And the approaches this application here and this program here are not necessarily the same. They're not the same. It's more difficult to distinguish between multiple classes than to distinguish between 2 classes. But you can use a binary classifier to build a multi-class classification, because you can distinguish one against all the others, and then from all the others distinguish one among all the remainers, and then take this one among all the remainers, and so forth. So you can use a binary classifier to build a multi-class classification. there's this idea of a single label classification. So each new object that I will classify with this model that I learned, each object will get only one label. It's a red, or it's a green, or it's a gray, or a blue. But there are other applications where you can give multiple labels to each new object. For example, I have here documents, and the documents I need to group them or classify them based on topic. Well, some documents may talk about 2 different topics at the same time, okay? Or even if you have medical images and you want to classify them based on the type of disease, well, the same patients may have two issues at the same time, not just comorbidities, we call two different things at the same time, not just one. There are other important notions to remember. When you build a classifier, this is what I represented here by the cloud, that cloud can be a black box. A black box, it means, well, I can't open it and see how it is used to predict. When it predicts, well, it predicts and I have to take it for face value. But there are other methods that when it generates a predictive model, that predictive model is actually transparent. It's not opaque like this black box, it's transparent. Transparent means that I can see the model, I can see what it learned. For example, if I have here rules, if I have A and B, then it should be green. If I have C and D, then it should be gray. If I have this feature F, then it should be red. Not only I can see it inside, but I could, if I have extra knowledge that wasn't expressed in the training data, but I'm an expert in this application and I know something else, I can actually edit this. That's why I'm representing the hand here. I can actually change the model that is learned, and then it makes it even better. Another important notion, most of the techniques to learn a predictive model, they assume that the data is balanced. Now here I have more or less 50-50, 50 green and 50 red, and I build a classification model, easy. But in many applications, it's not as rosy as in the labs when you do you build your code. In many applications, the data is completely imbalanced. The training data that is given to you is not balanced. And building this classifier to deal with this imbalance is a different challenge, completely different. And this is typical because, for example, when you go to a doctor's office, for example, and look at the patients that they have, let's say I'm looking at mammograms, the majority don't have any cancer. The majority are fine or benign. But if you go to a screening center where those patients are sent to be, well, actually it's the opposite. The screening, you will have more people who are fine than people who are with cancer. But if you go to the office of the oncologist, it's the opposite, because the office of the oncologist, most patients who are sent there, there's a high suspicion that they have cancer. So you'll find the balance, the imbalance in the other direction. So what you should retain is the fact that machine learning or supervised learning, you have an input, which is the training data, and you learn what the output is, a model, okay, whatever that model is. And the model becomes the input in addition to some kind of evidence that you observe, becomes the input to the box called prediction, and the prediction, its output is the prediction on that evidence, the new label that has been predicted with the model. So this is the typical framework for supervised learning. You have data that somebody labeled, an expert has labeled. That's not always easy to get, but once you have that, you split it into 2 parts. One part you use it for training, and another part you hide it, you leave it on the side. You don't use it for training at all. You will use it later for testing to make sure that what you learned actually works. So on the training data, you will build your classifier, and then you will use your testing data. You hide the labels, you pass it to the classifier, and you look at what the classifier has predicted, compare it to the labels that you have here as ground truth. And that allows you to estimate the accuracy. If the accuracy is not good, then you have to train again. Either you get more data, you split in different ways, you get another algorithm or whatever, until the accuracy is good enough for your application. When the accuracy is good enough for your application, then you can deploy it. You have new unlabeled data, and the classifier will be used to classify these new unlabeled data. Now, what is the acceptable accuracy? Well, it depends upon the application. If your application is about detecting spam and non-spam, well, it's not a big deal if it makes mistakes. If it makes mistakes, the cost is that you will use an email because it went to the trash, or you are annoyed by spam that you didn't want to see. It's not a big deal. However, if your application is to decide whether somebody has cancer or not, the mistakes are very expensive. The false positives, it's when, for example, a woman doesn't have breast cancer, but the predictor says she has breast cancer. Well, there's a cost, because there's a psychological cost first. You tell her, oh, you have cancer. Well, she doesn't. You will send her for a biopsy. That costs, and it's painful and things like that. The other way around is even more expensive. There's a woman who has cancer, and you tell her, this is the false negative, you tell her, no, you're fine, go home. Well, the cost can be death. So in that case, the accuracy has to be extremely high. We can't deploy an application when the accuracy is not good enough. So what accuracy we need depends upon the application. So there are many methods to build these, what I showed you here as a gray cloud, the predictive models. I will show you 3 of them. I chose these 3 because they're completely different, and they are intuitive to some extent, to show you how this can be done. So the first one is what we call the K-nearest neighbors. Second one is decision tree, and finally the neural networks. K-nearest neighbors is the simplest one. Actually, there's no learning whatsoever. This is what we call lazy learning. It's lazy because it's not learning. It keeps all the data, the training data, on the side. It may rank it, sort it in some way, and then it will use it each time it's asked to predict. So it's not building a model, it's the data set itself that is the model. How does it work? Basically, each time I have an object to classify, to predict its label, I will use it to compare it against all the objects that I have in my training data and look at which one is the closest or the nearest neighbor. And then the one that is the nearest to it from my training data, I look at its label and then I assign it to my new object. This is the case where I have only one neighbor. So here again, I have my training data. I have 2 classes, blue and red. I have a new object that I need to predict its label, so it doesn't have a color. So I will look at all my data here and see which one is the closest to this new entry. Oh, here it is. It's blue. Then I will assign blue label to this new object. To do this, I need to have a notion of a distance, the distance between one record and the other, one object and the other, a way of comparing them. In other ways, a function that I give x and y, and it'll tell me the distance between the two. And this way I will choose the closest, which is the nearest neighbor, and then I'll take the label and attach it to the new object. There is a variation of the nearest neighbor called k-nearest neighbors. So instead of looking at 1, I will look at k-nearest neighbors. In this particular case, I have 5, so k is 5, so 5 nearest neighbors. When I get an object, I look at the k-nearest neighbors. Oops, they may not agree. Some are saying red, some are saying blue. Well, I'll do a vote. I'll vote. I have 3 that are red, 2 that are blue, then I'm more confident as red, and I'll assign red to the as a label to the new object. This is very easy. It's called lazy learning because I'm not really learning. I'm waiting till I'm asked to predict, and then I compare with the training data that I have. It has many disadvantages because I need to keep all this data available. It takes time because I have to compare with all these. There are some variations, of course, I'm explaining at a very high level. But surprisingly, this very dumb and naive way can do very, very well on many applications, many data sets. Any questions about this? No reaction? No, that's fine.
Hello.
Yeah, go ahead.
So
John.
I guess you could also, can you, I guess, assign a priority to like the 5 closest neighbors, I guess? Like if this one is the closest neighbor, then it has more voting power than the rest.
Yes, you can. So it doesn't have to be democratic, one for each. There are many schemes. I told you this is the simplest way. There are many variations. There are agglomerative Knearest neighbors. There are many different add-ons to this. One of them is indeed having a more sophisticated voting scheme rather than they are equal 1, 1, 1. They can have, based on the distance, you suggested the distance, it can be based on other factors why this one has a higher weight than the other. That is definitely possible, yes.
Okay, thank you.
Okay, then I will continue. Yeah, oh, there you go. There's also weighted Knearest neighbors. You read my slide before. No, I'm just kidding. But that's exactly what you were asking about. Now I'll tell you about another technique called decision trees. So the model that we will build that represents the knowledge inside the training data will be a tree that will help us do decisions, and that's why we call it decision tree. So I'm taking an example from the original paper that presented the first algorithm decision trees called ID3 by Quinlan in 1983, so a long time ago. And in his paper, he was showing an example of weather conditions when he was playing or not playing tennis. So this is the training data. And he wants to build now a predictive model to predict whether I will play tennis or not play tennis given the weather conditions of today. So the weather conditions are expressed by outlook, whether it's sunny, overcast, or rain, temperature. He put them in 2 buckets, hot, mild, or cold, humidity, high, normal, or there's low, high or normal, they don't even have low, and then windy, is it true or false? And then this is the class label. Do I play tennis or I don't play tennis? So negative and positive. And on purpose, I put colors here. So the negative are, so I don't play is orange, and gray I have positive. So how do I build a decision tree? Well, first I'll call an oracle to give us a decision tree. Here's a decision tree that represents all the information that I have in my training data. Because you can see that if I ask the question, is it outlook, what's the outlook overcast? If it is overcast, I will always play positive. You see here I have overcast, I play. Overcast, I play. Overcast, I play overcast. I never have overcast that is orange. However, if the outlook is sunny, I have some sunny that are orange and I have sunny that are gray. So overcast sunny doesn't help me decide. I still have to ask the question about another feature, for example, humidity. If humidity is high, so you can see sunny and high, sunny and high, sunny and high is always negative. However, sunny and normal, I always play. Okay, so I am basically distinguishing between the N and P based on the values of these attributes. These are called attributes or variables. And based on the values, I will distinguish the two cases, negative or positive. And the same thing happened with rain. Rain, well, I have some cases of outlook rain where I play, and I have also rain where I don't play. So rain alone doesn't allow me to distinguish. I need to ask also a question about whether it is windy, true or false. And then that will allow me to distinguish between the positive and the negative. It happens that this is not the unique tree. They could have, we can build many different trees. Some trees are better than others. Why is it they're better than others? Because when I have, basically, when I have a new weather condition and I need to predict whether they play or not, I just have to follow the path here until the leaf node. This is what we call the leaf nodes. And that will tell me the prediction whether I'll play or not. So if I have a very deep tree, it'll take me many questions before I am able to predict. I don't want a very deep tree, but at the same time, I don't want to have a too shallow of a tree. So I need to find also a balanced tree, not a tree that is only on one side and not on the other side. So there are many different trees. Some are better than others. How do you find a good optimal tree systematically? And in his paper, he presents an algorithm to do it, a very beautiful recursive algorithm. And the algorithm idea is to take the whole data space of the training data space and try to identify, select one attribute that best separates that group of data points. And then using the values of that attribute, like for example, here I took the attribute outlook. What are the values? I have sunny, I have overcast, and I have rain. I will create branches and split that node of the tree. Originally, I have all the data points in one node. I will split by as many nodes as I have values for that attribute. And then I check if the class of all those new points in that new tree node are from the same class, then I will label that node with a leaf node with that class. Otherwise, I have to recursively select another attribute. Like here, I had to select another attribute, humidity, and split the data again. And I do that recursively, and I stop when I don't have, or when all the data points in the node are from the same class, or I don't have new attributes to select, or there are no samples in a particular value for that attribute. And this is guaranteed to finish and to give you a tree that is an optimal tree. However, there's a question here. How do I select an attribute? Well, here I selected outlook. I could have, from the beginning, selected temperature. I could have selected humidity first. So there are many strategies based on information gain and which one gives you more information by splitting the data into different nodes based on the values of that attribute. I won't go into the details, but just to remember that there are strategies to select the best attribute. And this guarantees you to find a tree. And once you have the tree, the beauty of this tree is that it's human readable. It's part of these classifiers that are transparent. It's not a black box. Each path in the tree can become a rule. The rule says, if outlook is rain and windy is false, then the class predicted to be positive. If the outlook is sunny and humidity is normal, then predict the class label is positive. So I can create rules. I can write this tree as a rule, a set of rules, and they're human readable. And you can change them too. So it's a very nice kind of model. It's not always correct. You have some redundancies in the tree. So there are techniques of pruning this tree to make it less dense and not overfitting the data and things like that. I will not go into details there. Now and how much time do I have? Just a few minutes. I want to talk about neural networks. neural networks is yet another way of learning a predictive model that can predict a decision, can predict a class label. And it's not new. It dates also from the 50s. And it's based on what we thought, and some people still think, the way the brain functions. So it's mimicking, to some extent, how the brain functions, except that we have different types of neurons, completely different. In the artificial neural networks, we typically will have only one type of neurons. It's a very rough simplification of how a single neuron works. So this is the artificial single neuron. What we have a cell here. Okay, a cell receives many inputs. So this is like a vector, x0 to xn, but these are the connections coming in to the sending signals to the cell. They have different strengths. So some are exciting, some are inhibiting. So you have weights. The weights can be positive or negative. Okay. This cell here may have some kind of bias. It adds something to the mixture, and at one point it will fire a message. This firing of a signal depends on an activation function that is triggered to send this the signal, and the signal will go to another neuron, another set of neurons, and it keeps on going. And this is basically the simplification of a real natural neuron. Typically what we have them connected by layers. Okay, so this is a neuron. The size here doesn't really matter. I have what we call an input layer. We have what we call an output layer, and we have a hidden layer or many hidden layers, and they have connections, and each connection has a weight. And the output layer is the prediction. The prediction that you want to have, is it the class A or class B? Is it cancer or no cancer? Is it spam or non-spam or whatever? The input layer is a codification of the input. For example, the medical image, for example, the email, or whatever you give it. And what it learns these weights, because these weights will tell you how the signals will be transmitted from the input to the prediction layer, the output layer. So it's basically a directed graph, because the signal goes from one direction to the other. Neural networks, it's not a perfect science. It has a lot of art in it as well, because you need to design a configuration. It's not necessarily fully connected. How many layers you have, how many nodes you have per layer, and so forth. It's not straightforward. There's a lot of trial and error in there. So it learns by example. I think you have it here in the next slide. You have, as I said, in the input layer, you have the input vector that is given, and then you have an activation function in each one of these. They will at one point send a signal to the next layer. The next layer will get, you see, you have these weights. So you have an activation function here as well. It'll send the message, and it'll go feed forward to the output layer. And in the output layer, we will compare it to what we were expecting as a label. Remember, I have here training data. The training data has labels attached to them. The example, I hide the training, I hide the label. I pass only the data without the label, and then here I get a new label that is predicted. I compare it to the label that I was expecting, and the difference between the predicted and the expectation will help me fix the weights here and backpropagate the correction of the error until I go back to the input. And I do that many, many, many times until the difference between the expected and the predicted becomes small. And then what changed are these weights. And that's what we learn. Now, when I have something to predict, a new object that hasn't been seen before, I'll pass it as input and it'll give me as output the label. So it's very similar to, but I said it's a simplification, it's very similar to a real neural network, because the neural network, you have these, the cells, you have the dendrites. The dendrites basically are this input vector. The cell at one point sends a signal, it can go to many different other cells, and that axon here is this, what comes after the activation function. Yeah, this is explaining what I was saying before. This is the training data. You see here the label. I'm not taking the label. I'm taking only the description of the data, pass it here. The output, the output, I will compare what I get here with the label, and then I back propagate the error to fix the weights on the edges. So this is neural networks. Today we're talking about deep neural network. Neural networks have many advantages. The one advantage is that their prediction, surprisingly, is amazingly accurate, is very good. They're very robust, even if you have noise in your data. However, they take a very long time to train. You have to iterate many times until they converge. So when you train them, you say, I said you have to do it many times. Either you stop after 1,000,000 times or something like that, or you stop when you have a small difference between the expected and the predicted. So they take a long time to converge, typically. Once they finish and they converge, what you learned are these weights. So it's very difficult to interpret them. It's not like those decision trees that a human can interpret. And if you change the weight here, it's very difficult to control the repercussion of that change. It's not like editing those rules or editing the tree. It's very difficult to edit. It's impossible, actually, to edit. So you can't incorporate your domain knowledge in them. And as I said, the design is very tedious. It's almost an art. If it's too small, it becomes slow to converge, slow to learn. If it's too big, then it's not stable and will overfit your data. So if you give it new data, it may not perform well, even though it performs well on the training data. Now, deep learning is a rebranding of this, except that we have many more layers than what we had before. But another difference is the fact that in the original neural networks, when you get data, and here, like for example, an image of an owl, I have to engineer the features that I extract from the image. For example, I don't know, the average of the pixels, how many areas I have. So I have to do some pre-processing of my input to engineer some features, and those features are given to the neural network. In deep learning, what happens is that I don't have to provide any features. The features are discovered automatically. I just have to code this in some binary form, give it in a very large vector, a binary vector to an input layer, and then the features will be discovered in these layers by the neural network itself. Okay. So this is a kind of a repetition. This is the typical neural network. In the past, we had an input layer, one hidden layer, and an output layer. Today, we have many hundreds, if not thousands of these hidden layers. And the reason is that we have the capability to do that. With these computers of today, this is plausible, but it wasn't a few years back. Now then, this is very simplistic. I'm showing a fully connected neural network. There are many different variations, different architectures for different purposes for deep learning. So what to remember is that in supervised learning, you have training data that has to be labeled by some expert. You learn a model. That model can be a set of rules, can be a decision tree or some data structure, can be mathematical formulae to distinguish between one class or another. It can be hyperplane dividing the space. It can be a neural network. It doesn't really matter. It's just a classifier that you will use to predict automatically the labels of new objects, new observations that you haven't seen before. Okay, so this summarizes my presentation, and if you have questions, we have time. Yeah, we still have a few minutes. So I'm going to stop this and see if you have questions.
Okay, are there any questions?
Yeah, I had a quick one. So the other lecture, we discussed about how certain programs outperformed human experts.
So sorry, in the previous lecture, I discussed about?
In a previous lecture, we discussed that in some programs outperformed human experts
Yes.
in identifying or running certain programs.
Yeah.
I was just wondering if there were any situations in a medical setting
Yes.
where
Yes.
the programs had a similar.
Oh yeah, there are many examples, especially with images. And other cases when you have also text and things like that, when you have a lot of data to digest, computers are better than humans, and particularly using deep learning. So the difference between deep learning and other methods is that the more data you give them, the better they are. I don't have the figure here, but imagine you have on the x-axis, you have the amount of data that you give, the amount of training data you give to the algorithm, and on the y-axis you have the accuracy, the performance. Most of the previous algorithms, the more data you give them, they get better, they get better, they get better, and at one point they reach a plateau. You give them more data, and yeah, they increase a tiny bit, but it's negligible. With deep learning, they keep on going and improving and improving and improving. And that's why at one point they surpass humans. So one example is recognizing melanoma. They're better than humans. Recognizing breast cancer and mammography, they're better than humans. But there are very interesting experiments. So people see that and they say, well, then we don't need radiologists anymore. Or pathologists. Kim's going to. Yeah, actually, it's not true. It's not true at all. And I love this experiment done at the University of New York, where they took 14 radiologists and they gave them a data set of mammograms, high resolution mammograms. And of course, they don't have all the same performance depending upon their experience and stuff like that. But on average, they have an average radiologist out of these 14. And they compare it to their machine learning, deep learning based classifier. Well, the deep learning based classifier does better than the average professional radiologist. But then they didn't stop there. What they did is they put a radiologist with this program, so two together, and they did better than the program alone. So that means that a radiologist with the tool in hand can do better than the machine or the radiologist, which is quite interesting result. So no, we still need radiologists. This is one example. There are many other examples where machines can do better than humans. And it doesn't mean that the machine understands. That's another big problem. A radiologist, when they say this case is A or B, that's my prediction, my diagnostic, for example, you can ask them why. They can explain the reasoning they went through to decide whether this has cancer or doesn't have cancer or whatever. They can explain their decision. The deep learning that does better than the human is a black box. When you ask it why, you get nothing out of it. You'll get these weights and these connections between the neurons. They mean nothing. Okay, and that's a big problem. Now, if a human and this tool work together, you can still have the explanation of the human. And remember, the human and the tool, they do better than the average human, and they do better than the machine. Does it answer your question?
It does, yeah. So
Good.
do you think the reason why the combination of the machine and the expert, why it's better, is just because the human can take the information that the machine provides, then provide an explanation to why that is the case? Or is it an actual...
It can be many different factors, and that's something that needs to be studied. I don't have the answer to it. It's something that actually Garry Kasparov, the one who lost against Deep Blue, he wrote a book about it. After losing against Deep Blue, he went through depression. It was a big deal, even though he got the $1 million from from IBM. It was a competition, but paid competition. He was depressed, and when he came out of the depression, he started thinking about it, and he was impressed by these machines, and he started playing with the machines, and he realized that actually working with the machine, because you could have a machine against a machine, working with the machine, he was able to beat the machine. And he wrote a book about collaborating with the machine to do better. I forgot the title of the book, but it's not just in this example of mammography. In other examples, humans working with the machine can do better. And why? It's a very good question that requires more study. I can speculate, but I'm not sure exactly how. And it probably depends upon the application too.
Yeah, it's kind of interesting to think about.
Definitely interesting question, yes.
Yeah, thank you.
So we think of this as a situation where, you know, there's a certain percentage of getting things right or wrong, but there's another side of it, just moving life forward. And actually everybody on the call, I think, is beginning to have experiences like this. There's something that you want an answer to, and it's something that has both humans working in the entity and some sort of interface where you enter text and then go from page to page. And if that entity is understaffed with humans, you can get a lot of answers just from the algorithm of the page where you're entering data. See what happens when you enter a certain amount of data, it goes to the next page. What is that? And often exactly what you wanted to ask the people and you can't get answers to, it becomes obvious from that interface. And that's not a matter of right and wrong. It's a matter of sort of getting things done. And normal life today is sort of a combination, right, of interacting with not necessarily sentient machines, but, you know, machines that can get you to the next point, and human beings. We're working for the same companies. And it can be frustrating that the standards for people getting back to you when you ask a question in a situation where most of those questions can be answered experientially, just going into the forms and entering data. The human responses get slower and slower because the humans think, well, that's obvious from the form. Like, can you use different email addresses? If you enter data that the form doesn't like, then that is flagged in some way, or it's yellow rather than black and white. So you can instantly tell if there's something about your answer that the system doesn't like. And it's a lot quicker than calling up a human and asking, can I use more than one email address? You know, does that work for your system? So we're not talking about something here abstract and separated from us. This is very much an integral part of every single day of everybody living on the planet now. Yeah.
Yeah. And humans can be very frustrating.
Yes. Yeah. And it'd be hard to have this kind of customer service job where almost every question somebody asks you, they could answer in a second by just entering text somewhere. So you seem redundant. They may not realize that you're redundant, but you're slower, you're less capable than entering text, you know? So, yeah. Other questions? So speaking about not knowing things and uncertainty and important things in your life, next Tuesday is very important in your life. It's the most consequential day of the course, probably, with Rich Sutton teaching. And there are a number of things about it. Some of these may surprise you, shock you, but it's just the way it is, folks. So we don't know for sure that there will be face-to-face teaching, but we think so. And it's in
Not next week. Not next week. Next week will not be face-to-face. It'll be online.
Okay. Well, all right then. But anyway, eventually, those of you who want to be in the room, we're going to need to know your COVID status. And if you think about this, do we have the right to know this? The legal answer is like this. AHS allows the university to be the custodian of that data. So the university already knows a lot about your health and other things. So one way or the other, by telling me or filling out some standard form, in the future, when we have part of the course face-to-face, we will need to know your COVID status, that you have had 2 vaccinations for you to be in the room. And that's not just the students getting credit for the course, it's also the TAs, the people teaching in the course, everybody in that room. We will need to know your COVID
Vaccination.
status. Yeah. So Osmar, tell me about this. The official Central University communications said that this day there would be no face-to-face teaching. There would be an exemption for entities that could provide proof of COVID status starting on the 20th, which is Monday. Now, is there something in the Faculty of Science different from that?
Yeah, each faculty may be different. So basically today, all the online, face-to-face courses were canceled and moved, if possible, to online. You were ready, so it's not an issue. And up to 2 weeks they will need to implement a way to verify the vaccination status of visitors and students and staff coming to classes and labs.
Right.
So they may be ready by Monday if they reach an agreement on a way to implement this verification thing.
Yeah, yeah. So
they told faculty members to expect up to 2 weeks.
Right, yeah, but it could be as short as Monday the 20th.
I'm not that optimistic, but it can be.
Right. So for our session with Rich Sutton, just to give you an idea of the importance of this, that his latest paper, entitled "Reward is Enough," is very widely quoted. He is one of the best known AI people in the North American continent. And he intends to update his statement, which is, a required part of the exam for all of you, his beliefs about AI safety in the future. That's in that slide from my earlier lecture. So he will update that. I think it'd be quite a fascinating teaching session. But I still don't quite know its character. I know what he wants, I know what I want, but I don't know what the external environment will do to those things, you know? And you may wonder how this came about. He and I live close to each other. And it used to fascinate me that in the days when he ran or jogged, that my house was the turning around point for his jogging. And I was astounded to find, and it's not, I mean, he was actually turning around in our driveway, you know, so on. Yeah. So I was mowing the lawn.
Stepping on your turf.
Yeah, mowing the lawn a few weeks ago. And now he doesn't jog, he walks the same route. And we had the most consequential conversation that I think I've ever had in my life, where in about 15 minutes, we solved a whole bunch of things. He hadn't taught in the course for a long time, and he agreed to teach this term and to bring us his current 2021 feelings about these things. And we also talked about this idea of mine of AI expanding its current purview to sort of solve the big 6 to 8 problems of the human race. And he sort of agreed that one of the problems in the AI field at the moment is that there have been some spectacular successes. And so people keep doing similar sorts of things in those areas rather than branching out to try something messy and new. So dealing with human problems associated with a lot of suffering and, you know, injustice and so on, that adds a whole new area of, you know, complexity. But he is interested in that, and he feels that this course is performing a public service, interesting a lot of people in AI who would not otherwise
Be exposed.
have that interest. Yeah. So I'm pitching it to tell you how interesting it is. But if we do have face-to-face, I don't want more than about 5 of you in the room. So yeah, and we would certainly need to know the COVID status of those 5 people. So any questions about that?
No, I actually did have a question for Dr. Zaiane.
Yeah.
Mhm. I'm still here.
Yes, you are. So I'm a little bit confused about how exactly a decision tree like improves upon itself, like using more examples. Is it like it
No,
is an
doesn't-
AI, right?
doesn't improve upon itself. No.
Okay.
No. So you have all the training data,
Mhm.
okay, and you look at the training data recursively. So means that all my data, I put it in one node of the tree. It's what we call the root node, the top node.
Okay.
Our trees are upside down. The root is on top and the leaves on the bottom, but it doesn't matter.
Mhm.
So I put all my data in one node, and I check, do all the points in my node predict the same, or they have the same class? If not, then I have to split them. What is the attribute that best splits them on these different values? And then I will take that data that I have in my node and break it down into as many new nodes as I have values for that attribute that I selected. How to select the attribute is a different story. And then every single new node, I will check if they are in the same class. If they are in the same class, then I stop and I label that class with its class. If they're not, then I do exactly the same thing. I choose another attribute that splits them. So I don't improve upon myself. I just start with the whole data set and I'm splitting. Basically, I'm dividing the space of the data until I build that tree. And I stop. Once I build that tree, I stop. I'm not doing any improvement anymore.
Oh, I see how it is. Okay. So Wait, can you build a program to make decision trees, or you have to
Yes,
like
yeah,
use
yeah,
a
yeah. That's what the algorithm is
Oh.
a recipe, basically. The recipe is the program saying what to do if I have this data. If I change the data, the tree will be different. But this process that I just described is the algorithm and guarantees that I have an optimal tree, not a tree that is imbalanced or too deep or something like that. However,
Oh.
I passed a step that I didn't explain very well, which is how do I select which attribute best splits a data set into classes. That selection is using information theory, and I didn't go into the details there. So we use the notion of information gain. So which attribute gives me more information by splitting. So I'm trying to use layman's terms here, but there are mathematical formulae from information theory that allow me to select the best attribute to split my data.
Oh, okay, I see. Yes. Okay, thank you.
You're welcome. Well, have a wonderful, restful weekend.
Yeah, and we'll see what happens next Tuesday. Whatever it is, I predict that you'll all enjoy it very much. Tasmin, yes.
Oh, there's a question?
Yeah.
Oh, that was just applause.
Oh,
Oh, thank you.
applause. Okay. All right. I agree. Okay. Applause. Okay. Yeah. All right.
You guys stay healthy.
Bye-bye.
Yes, bye-bye. Thank you.